Okay, we'll start the session. So, good evening, good evening, everyone. This is live discussion session of problem solving for session number 8 for the course entitled Basic Thermodynamics, Classical and Statistical Approaches. This course has course code NOC 24CY04 and myself Akash Gutal. I'm PhD student in Department of Chemistry, Indian Institute of Technology. So today uh, we are going to discuss some some aspect, the revision aspects of last week's NPTEL videos, and there are some few problems that practice problems that we are going to solve. Uh, First, we will do a revision, whatever we have done last week. So, so last week we started from most probable distribution. Most probable distribution. So, what is the most probable distribution? The distribution for which the number of microstates are maximum. So W tends to W max. So that uh, distribution is we referred as most probable distribution of a given system. So due to its large W value, that is the number of microstates value, its entropy is highest. It's having highest entropy. and and that's the reason for the spontaneous process also, because the system always goes towards the distribution where these microstates are maximum. That's why we found that entropy always increases uh, in the thermodynamic spontaneous process. So we have discussed the two level system. For two level system, so there are only two levels, E naught and E1, let's say. And that two level system, the distribution of a particle is the we will say the most probable distribution for the two level system. I will directly write the formula we have discussed in the lectures. N factorial divided by n by 2 factorial into n by 2 factorial. Right? This is the maximum distribution for two level system. Fine. So this is the uh, most probable distribution for two level system. Then, if suppose we are having n particles are distributed in r levels. N particles are distributed, suppose in r levels. Then the number of microstates, or we can say the maximum number of microstates, uh, not maximum. In general, number of microstates are n factorial divided by n1 factorial, n2 factorial into n3 factorial, and that's just up to the nr factorials. Okay, and this is the formula. So in this case, in two-level system, in general formula reduces to n factorial divided by n1 factorial n2 factorial for two-level system. For n-level systems or r-level systems, it's only divided by n1, n2, n3, n4 up to nr factorials multiplication. So let me add one more slide. So, so suppose we are having multiple levels, and we need to find out the number of distributions. Suppose, and this is problem of what we had said is have said is it's a problem of uh, partitioning. Okay, this is the proper problem of partitioning of the n particle in r levels is can be given as k is equal to 1 to n p n k. Hmm? P is the partition at kth for n particles for given total number of r. So if we are having large n, if n is very large, then this partitioning number of partitions are approximately equal to 1 upon 4 pi root 3 exponential pi 2 pi by 3. So this is the general formula. Then we have discussed formula for particles are distinguishable and box boxes or energy are indistinguishable. And we are having n particles and r levels. So how many microstates we will be having is formula is given as r plus n minus 1 c, which is combination, n minus 1 for r level and n particles. Fine. So this will be your W, number of microstates. Then we have seen, let me add one new slide. So we have seen the number of possibilities. So if we are having number of partitions equal to number of distributions, and given the total energy and not, and number of ways a particle occupies an energy level I is can be given as Wi is equal to n minus 2 plus n naught minus I whole factorial divided by n minus 2 factorial n naught minus I factorial. And this is the formula that we have seen. And the last part that we have discussed is the Maxwell-Boltzmann distribution. Maxwell-Boltzmann distribution, which says that number of particles in ith level divided by number of total particles are equal to, this fraction is equal to A into e raised to minus b epsilon I, where epsilon I is the energy of ith level. This is from this equation we have derived Maxwell-Boltzmann distribution. So this is the Maxwell-Boltzmann distribution. Properly. Fine. This much we have done last entire week, and now we are going to solve some problems related to these aspects. So the first problem will start. The question number one is, what is the number of microstates in the following distribution? So quanta and distinguishable particles are given. The distribution is given. We are asked the total number of microstates in the following distribution. Okay, we have seen the formula. So please try to solve this. I will give you 2 to 3 minutes. And if you need more time, you can pause this video and try to solve by yourself and then check the solution part. So this problem is actually related to the same thing, which is you are having n number of particles. You need to distribute in the r number of uh, levels, energy levels, and particles are distinguishable because they are denoted by the colors. You can see that they are denoted by colors, which means they are distinguishable. The same formula that we have discussed, the number of microstates, n factorial divided by n1 factorial into n2 factorial into n3 factorial up to nr factorial. Same formula we need to use. All other things are there. So, so we know the formula is W is equal to n factorial divided by n1 factorial and 2 factorial up to nr factorial. So here r is equal to 5 and n is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. N is equal to 9. Fine. So W is equal to 9 factorial divided by n1. Sorry, what is the value of n1? It is 1, n2 is 2, n3 is, let me do it in this. When 1 is equal to 3, and 2 is equal to 0, and 3 is equal to 1, and 4 is equal to 2, and 5 is equal to 2, and 6 is equal to 1. So we have 3 factorial, 0 factorial, 1 factorial, into 2 factorial, into 2 factorial, into 1 factorial. Hmm? So W is equal to, so this, and this 3 factorials will be 1. So then we will be having 3 factorial into 2 factorial into 2 factorial. This can be written as 9 into 8 into 7 into 6 into 5 into 4 and cross 3 factorial divided by 3 factorial into 2 factorial into 3 factorial, 3 factorial get cancelled. And 2 factorial is nothing but the 2 itself because 2 cross 1 is 1, 2 cross 1 is 2, and we can directly take out 2 to the 4, 2 to the 6, 9 into 8 into 7 into 3 into 5 into 2. So that should give you the answer, which is nothing but if you calculate it, you will get 15, 1, 2, 0. So number of microstates are 15, 1, 2. Option number is B. Fine. So let's move towards the second question. Question number second. How many arrangements are there of 20 distinguishable lattice gas particles distributed on 23 sites? So how many arrangements are there of 20 distinguishable lattice gas particles distributed on 23 sites? Let's try to calculate. The hint will be it's just combination uh, problem. Solid by combination. Take 2-3 minutes. So the answer would be we can find out by using uh, we have, let's say, the what question is saying is how many arrangements are there of 20 distinguishable lattice gas particles distributed on 23 sites. Suppose we are having 23 sites and we are having 20 gas particles, which means so each site can occupy only one uh, gas particle because it's a lattice system. So that's why we can calculate uh, the number of arrangements are n number of gas particles c. Uh, suppose these are L lattice points and 20 are the n and c, sorry, LC n, which is nothing but 23C 20. How many combinations can we can get from 23 lattice side uh, which are having 20 uh, unique arrangements. So that can be given as 23C20, which can be obtained as 20. One second. 23 factorial divided by 20 factorial into 23 minus 20 factorial, which is nothing but 23 factorial divided by 20 factorial cross 3 factorial. Oh, so cross 3 factorial, which we can get 23 into 22, 21 into 20 factorial divided by 20 factorial into 3 factorial, which will get, I will write this state here, is equal to 23 cross 22 cross 21 divided by 3 cross 2 cross 1, which gives 11, 3, 7, it's nothing but 77 cross 23, which is nothing but is 1771. So your number of arrangements are, so number of arrangements 1771. Write it properly. 1771. Fine. Answer should be answer number C. Fine. The next question. Question number 3. Which of the following distributions have the highest number of microstates? So there's or the 4 level system is given and the distributions of the distinguishable particles as A, B, C, D are given. You need to find out what distribution having the highest number of microstates. So please try. I'm giving this 3-4 minutes. Try it by yourself. This also will be using the same formula. We have used it. It's simple. You calculate and if possible, tell me the answer. So let's calculate microstates for each system. Let's say first A. A will be having W number of microstates. The number of particles, first we will calculate what are the number of particles. N is equal to 1, 2, 3, 4, 5, 6, 7. So N is equal to 4, 6, sorry. N is equal to 6. For every system, I think N is equal to 6, yeah. So for all N is equal to 6 and W for A is 6 factorial divided by 3 and 2, uh, fourth and third energy level having only one particle and ground state having 4 particles, which will give you 6 cross 5 cross 4 for 4 factorial cross 4 factorial. Factorials get cancelled. These are 30. Number of microstates are 30 for A. For B, similarly, we can calculate number of microstates are 6 factorial divided by 2 factorial, 1 factorial, plus 3 factorial. So that will give you 6 cross 5 cross 4 cross 6 factorial divided by 2 factorial, 1 factorial, 3 factorial, 3 factorial get cancelled, and 2 to the 4, 6 cross 5 cross 2, which is 60. Microstates for B is 60. Similarly, for C, number of microstates can be given as 6 factorial divided by 1 factorial cross 2 factorial cross 3 factorial, which nothing but same as that of, so these both are the same, 6 cross 5 cross 4 cross 3 factorial divided by 2 factorial, 1 factorial, 2 factorial, 3 factorial plus 1 factorial, which will be the same, 6 cross 5 cross 2, that number 60, 60 number of matrices. And for system D, let me write here, for system D, we'll be having number of microstates is D, 6 factorial divided by 1 to 5 factorial cross 1 factorial. So that is 6 cross 5 factorial divided by 5 factorial into 1 factorial. 5 by it cancelled, which is only 6. So what we are having is number of microstates for B are equal to number of microstates of C, and these are highest, which is number 16. So these two will be having highest number of microstates. So hence the answer is option number D. Fine. So the next question. You have a one-dimensional lattice that contains Na particle of type A and Nb particles of type B. They completely fill the lattice. So the number of sides is Na plus Nb. What is the entropy of the distribution then? Hint, using Stirling approximation. So I will write here what is the Stirling approximation. You must have seen in the uh, lectures also that the Stirling approximation is, suppose you want logarithm of n factorial, which turns out to be n into log of n minus n, for, and this is only valid for n is sufficiently large. This is valid for n is sufficiently large. So by using this Stirling's approximation, you need to solve the problem. Please try it. I'm giving it 3 to 4 minutes to just work out and try to find the answer. So here K is KB. Remember that KB is Boltzmann constant. Remember this question can be solved by having considering the property of entropy. It's additive property. So you want to add the entropies of two systems. We okay. If you are mixing two systems or adding two systems, then the entropy is also added. This particular entropy property we need to use to solve this problem. So let me first add new slide. So right, we will be requiring okay. Then first to understand the problem. So we have one-dimensional lattice that contains Na particles. So here is one-dimensional lattice. Let's say in each lattice point there are one particle. So there are Na particles there, and there is another system with second with Nb particles. Fine. And that and this completely fill the lattice. So the number of sites, so they completely fill the lattice. Suppose so we combine these two. Uh, let me represent by another way. Hmm. Let me represent it another way. One dimensional lattice means, let's say, in elliptic lattice, it's only one dimensional. And so so let's say an A1 and A2 and A3 and A4, like this. We are having multiple NAs and B and B1, 2 and B3 and B4 and so on. They're having a random arrangement, and we are NA and NB, and the lattice is complete when we are having we add this both the sets NA and NB sets. So so whatever we are having, we know the total number of sites will be Na plus Nb to form our entire lattice system. Okay? And we need to find out what is the number of, we need to find out what is the entropy of distribution. Okay? We know what is the entropy, the Boltzmann famous equation, AB into ln number of W microstates. And for number of microstates, we have formula total number of particles divided by number of occupied N1, N2, and so on. In this case, we are having W and A plus NB will be the total number of particles, which is nothing but Na plus Nb. And we are having an individual lattice uh, of type A and type B. So that will contribute to Na factorial and Nb factorial. Fine. So this is our number of microstates for Na plus Nb lattice. So we need to calculate what is the ln W, the natural log of number of microstates. So there we will be going to use this Stirling approximation. Fine. So we'll be having mm, ln, that is natural log of number of microstates, is natural log of Na plus Nb factorial divided by Na factorial and B factorial. Fine. So by log rules, we'll be having ln let me write this in this way: Na plus Nb factorial minus ln and A factorial minus ln and B factorial. Fine. Now these are three different natural laws of factorials. We will apply the Stirling approximation. We know what is the Stirling approximation. That is, yeah. So you know what this Stirling approximation is? I have written here ln n factorial is, sorry. So we have applied to every uh, natural log Stirling approximation is we'll be having NA plus NB to ln NA plus NB minus NA plus NG. Similarly, ln so on NA into ln NA minus NA uh, minus NB ln NB minus NB. Hmm? For NA and NB is sufficiently large. So we simplify it. NA plus NB ln NA plus NB minus NA plus NB minus NA ln NA plus NA minus NB ln NB plus NB. So we will find this NA and B. We can add, and this Na and Nb are plus, and minus Na plus Nb is both are minus. So they will be get cancelled. This will be cancelled, this will be cancelled, this cancelled. So what is left? What is the left is Na plus Nb and Na plus Nb minus Na ln Na minus Nb ln Nb. So this is the value of ln W. Once we got the ln W, we will put this in entropy equation by the entropy Na plus Nb will be Kb into Boltzmann constant into whatever the ln natural log of that we found for number of characteristics. A ln Na minus Nb ln Nb. So this will be the answer. Right? So the option number is Na plus Nb ln Na ln Na plus NB minus Na ln Na minus NB ln Na. So our option number is A. Fine. So fifth question is, how many ways can you partition the integer 7, that is P7? So you need to find out how many ways you can partition the number 7, integer number 7. Please try it. I'm giving you 3 to 4 minutes. Please try and work out by yourself. So we have given, we need to find out the integer is 7, 7, and we need to find out what are the partitions of the 7. Let's try. P 7, 1, only one element are there. So is this will turn out to be only 7 itself is one partition. Let's say P 7, 2, which turn out to be, let's partition it, 6 plus 1, fine, 5 plus 2, 7, 4 plus 3. And if you try to reduce again 3 plus 4, that will be the same thing. Or 2 plus 5 will be the same thing which is previously written. So only three partitions can be possible in case of two uh, different using two different numbers. For 7, we partition with 3. Let's for 7 and we are partitioning with 3. Let's start with the maximum to minimum, which is, let's say we're having, let's say 5, 1, 1. So I should write it 5, 1, 1 plus 1 and 4 plus 2 plus 1, and then we'll be having 3 plus 3 plus 1, and we'll be having 3 plus 2 plus 2, right? And for 7, 4, so you need to uh, very careful about it because it should not repeat. Similarly, you will start from maximum to minimum. 4 plus 1 plus 1 plus 1. We need to we need to partition it into four different numbers. 4 plus 4, 4 plus 1 plus 1 plus 1. Then we will be having, let's say, if you reduce 4 once by 1 and add 1 to the next number, that will be 3 plus 2 plus 1 plus 1, 2, 3, 5 plus 1, 6 and 7. Right? Again, if you try to do it, then that will be the same thing. Okay, 3, 3 and 2, the same thing will appear. Instead of that, we will remove one number from 3 and add to third number. What will we get? Well, what will we be getting? 2 plus 2 plus 2 plus 1. Okay, that will be the new partition. I think if you now onwards, if you change anything from any number, that will be the same partitions that we got before. Fine. Or P75. So that will be 3 plus 1 plus 1 plus 1 plus 1. Right? And if you reduce 3 by 1 and add to the next number, that will be 2 plus 2 plus 1 plus 1 plus 1. 3, 4, 5, 6, 7. Right? There are only two possibilities. Then we are having P6. Let's try for P6. Sorry, 7 and 6. Let's try 2 plus 1 plus 1 plus 1 plus 1. 1, 2, 3, 4. 2, 3, 4, 5, 6, and 7. 2, 3, 4, 5, 6. Yeah. And is it other possible? Is there anything possible other than this? Uh, I think it's not. So last would be P7 with 7 number partitioning is itself 1 plus 1 plus 1 plus 1 plus 1 1 plus 1 1 2 3 4 5 6 7. And so these are the number of partitions. Let's count. This is total number is 1. This is 3. This is 1 2 4. This is 3. This is again 2. This is again 1. This is 1. So what is the total? 3 plus 4, 4, 4 and 4, 8. 8 and 3 is 11. 11, 12, 13, 14, and we will be having 15 number of partitions. So answer should be option number A, D. Fine. Next question. If there are 7 quantum energy partition against 5 distinguishable particles, find the total number of possibilities. So you need to find out and the total number of possibilities. Please try to work on this problem. Take 2-3 minutes, take your time and try to work out the given problem. This can be solved by standard formula. It is discussed in the lectures. So we know that suppose R quantum of energy, which is energy itself is indistinguishable. Energy itself is indistinguishable, and it is if it is partitioned against n particles, so the partitioning will be n plus sorry, r plus n minus 1 c n minus 1. Okay, this is the formula. Same thing, c is the combination. So we are having r is equal to 7 and n is equal to 5. So what will be getting? 7 plus 5 minus 1 c 5 minus 1, which is nothing but 7 and 5 is 12 minus 1 is 11 c 4, which is nothing but 11 factorial cross divided by 4 factorial, which is nothing but 11 10 uh sorry 4 factorial divided by 11 minus 4 factorial, which is sorry cross 9 cross 8 cross 7 factorial 4 factorial 7 factorial 7 7 get cancelled, and 11 cross 10 cross 9 cross 8 4 cross 3 cross 2 cross 1, which is 4 8 3 3 is 9 5 is 10. 55 into 3 cross 2. 55 into 2 is 1110. Cross 3 is nothing but 330. So your answer should be 330, option number A. Fine. It's simple. So next question. Consider a system consisting of subsystems A1 and A2, for which W1 is equal to 1 into 10 raised to 20, 10 raised to power 20, and W2 is 2 into 10 raised to power 20. What is the number of configurations available to the combined system? So W1 and W2 for A1 and A2 subsystems are given there, which means microstates are given. Then you find out their combined system microstates. Please work out. Take your 3 to 4 minutes and tell me the answer if possible. It's the same postulate that entropy of the two systems, if we add them, it's additive. So this problem, so we have W1 is equal to 1 cross 10 raised to 20, W2 is equal to 2 cross 10 raised to 20. And so we need to find out number of configurations available for the combined system. So we add two systems, their entropy relation will be SA1 plus SA2. SA1 plus A2 is equal to SA1 plus SA2, which is nothing but KB ln WA1 plus A2 is nothing but KB ln WA1 plus KB natural log of WA2. KB get cancelled, where I have natural log of WA1 plus A2 is nothing but ln WA1 plus natural log of A2. So you put these values, which will get the natural log of 10 raised to 20 plus natural log of 2 cross 10 raised to 20. So what we will be going to get? So what we can do is we can convert to first this natural log to log to the base 10. If you convert the log to the base 10, you need to multiply by 2.303. For so for this equation, both the sets are natural log, and the 2.303 also cancels out with KB value. So we can say we can write it log WA1 plus A2 is equal to log of WA1 plus log of WA2. Similarly, what will get here? Log of 10 raised to 20 plus log of 2 cross 10 raised to 20. So what we'll be having is 20 plus log of 2 plus 20, which is nothing but, okay, we can write, not, we should not write like this. We should not, log of 20 plus, this is plus sign. If you plus means log of 2 cross 10 raised to 20 into 10 raised to 20. So we will be using log properties of log, and log WA1 plus A2 will be this. And if you take anti-log on the both side, anti-log of log, I will write directly. If you take anti-log, this log will get cancelled. I will get WA1 plus A2 is equal to 2 cross 10 raised to 14 So 20 plus 20 is 40. And this will be the answer. Option number C. Fine. So the next question. There are three distinguishable non-interacting particles in a 3D box of length L, and the total energy is fixed at 33 H H square divided by 8 ml square. How many numbers of microstates are possible? Please take your time and calculate the number of microstates. Take 2-3 minutes. Try to solve by yourself. So in this problem, we are having three distinguishable non-interacting particles. Denote it, let's say there are three distinguishable non-interacting particles. So these are three particles in 3D box. We know that three-dimensional box, particularly in 3D box problem. Fine. So particle in 3D box, we are having quantum number nx, ny, and z, which gives you, which is proportional. So we know the energy expression, which depends upon nx, ny, and z, which is nx square plus ny square plus n, sorry for that, nc square into h square divided by 8 m l square. Fine. And we need to find out, and each uh, particle will be having energy uh, according to the energy levels of three-dimensional box. So what are the energy levels? If you see, The energy levels of three-dimensional box are, for each particle there will be in units of 8 ml 8 ml square divided by h square. In units of this, we are having energies as 3, 6, 9, 11, 12, and 14. You can find it in your lectures. In lecture, there is one table. You can find these values in that table. And we know their degeneracies. Their degeneracies are, for first level, the degeneracy is 1. Second level, the degeneracy is 3. Third level, degeneracy is 3. And for 11, the degeneracy is also 3. And for 12, it is 1. And 14, it is 16. Oh, sorry. 14 is, I think it is 6 or 6. Yeah. So let me check it once again whether degeneracies are right or not. So for 3D box, uh, for 11, there is a 3. And for 14, I think there must be 6 degenerate states. Right? There must be 6 degenerate states. So I will show you. I think it's better to show you the table. I think it's here. Controls. So the table is so this is the table. Okay. Is it visible? So we have here so we have here uh, this table. We have six degeneracy. 1, 3, 3. It's a 3. It's a mistake. I think it is not 1. It's 3. And 14. For 14, you can see uh, for 14E, it is 6. Okay. So we are having 1, 3, 3, 3, 6 degeneracy. Sorry, 1, 3, 3, 1, 6 for 3, 6, 9, 11, 12, and 14 energy bits. Okay. So we are having that. So each particle can have this range of energies. And we are provided the total energy is always constant with is total energy E is actually 33 H square by 8 ml square. Fine. So we need to assign these three particles to the energy levels of the particle in the box such that the total energy will be 33 H square by 8 ml square. 8 ml square. So this is we need to partition and if you see properly, so particle first, suppose it is having 11 unit of energy. Particle second, if it is having again 11, and third again 11, that will cause 33 H square by 8 ml square. Again, this is a one combination. And we know the 11, 11 having 3 degeneracy. Okay. The degeneracy is 3. Fine. So the degeneracy is 3 for 11. Similarly, there is one more combination, which is nothing but 9, 26 into 20, sorry, 9, 12, and 12. 24 plus 9 is 33. Okay. But 9 is having 3 degeneracy and 12 is having 1 degeneracy. If you see, only one pair triplet of quantum numbers are found for 12 unit of energy in this particular box. So we are having the system. So we can draw uh, the diagram that will be more clear to you. Let me add one more slide. So we'll be having energy levels in such a way that let's say it's 0, ground state 0. So 3, which is 3 is having multiplicity 1. Then we are having, let me draw smaller. This is 3, sheet E. This is 0. This is 3. This is 6, which is having degeneracy 3. Then we have 9 unit. Then we are having 11. Then we are having 12 and 14. Okay, this is 6 degenerate, 14, this is 12. So each particle can have the respective energies in three-dimensional box. So what combination we found? Let's say one particle is at 9 and two particles at 12. Similarly, this is the first one combination, and the second one is this is all the particles at 11 energy value, unit value. Okay, these are only two combinations are possible for 33 unit of energy. Yeah, only 33 of unit of energy. So, we will calculate the number of states. Okay, this here the first case we are having two distinguishable particles at 12 and one distinguishable particle at 9, which means this having flexibility of having three different positions, and other twos are having position, only one position. So our total number of combinations we can get are nothing but only three combinations. Either this must be here, here, or here, and these two, if they are distinguishable, so even we interchange them at the same energy level, there will not be uh, having any difference because they are at the same energy level. If you are having degeneracy, then that would be different aspect. So we are having only three. Uh, so for this aspect, we are only having three combinations. And for 11, if you see, for 11, for each particle can have degeneracy 3. In case of 11, each particle can have degeneracy 3. Okay, all three are at 11. So at 12, then, and hence the total number of combinations we can get is 3 plus 3 plus 3, 9. Okay, and whatever the total number of combination will be, and okay, and means multiplication. So total number of combinations, which means total number of combination in the sense total number of microstates, is 9 cross 3 because they themselves can arrange, which is nothing but 27. And your answer must be 27. Fine. So second last question is, in how many ways can two indistinguishable particles distribute among two distinguishable harmonic oscillators in a such a way that the total energy is fixed? So before that, we will having very less time. We just do, let's say, the last problem. Which of the following statements are incorrect? The number of microstates in the first and second excited states are equal for particle in 3D box. As the energy of the state increases, the number of particles in the state decreases according to Maxwell's Boltzmann law, and the distinguishability of the particles does not affect the number of states available for a system. And last one is all of them. Please try to solve. let's give 2-3 minutes to analyze this problem and solve. The number of microstates. So let's solve because we have less time. And the number of microstates in the first and second excited states are equal for particle in 3D box. So in the previous question, we have seen that this is your first excited state. This is your first excited state, and this is your second excited state. And if you see the degeneracy is the number of microstates in the first and second excited states are equal to the particle in 3D box. The degeneracies are itself are the number of microstates. So this first statement is right, and we need to find out incorrect statement. Okay, as the energy of the state increases, the number of particles in that state decreases according to the Maxwell-Boltzmann's law. So we know that Maxwell-Boltzmann law is suppose particles in an ith state, ith level, you can say, and divided by total number of particles is nothing but a dot e raised to minus b epsilon I. Okay, so this is e raised to minus b factor minus b epsilon I. Epsilon I is the energy of the that state. Okay, so what the statement saying is as the energy of the state increases, as E increases or epsilon increases, epsilon I increases, then the particles, number of particles in the state decreases. So number of particles, this fraction, the fraction in this case, the fraction is decreasing. So let's check epsilon I if increases, the e raised to minus bi get decreases. Once the decreases, the fraction will decrease. So the statement, if energy increases, then the number of particles in the state must decrease. So the fraction which is decreasing means Ni is itself decreasing. N will not going to change because N is the constant. Because the number of particles, let's say constant if we are studying a particular system. So Ni will be reduced. So the number of particles in that state will of course decrease. So the second statement is also correct. The third statement is the distinguishability of the particles does not affect the number of microstates available for a system. So this distinguishability of particles does not affect the number of microstates, which is not a proper statement because once the particles are distinguishable, they're even they are in the two different states. The combination of the uh, exchange of the two particles. Suppose there are two level system and two particles, and the particles are distinguishable. Then the particle, suppose particle one at the excited state and particle two at the ground state will be, and vice versa. These are the two different states because these two particles are distinguishable. So we can distinguish them when two is at the excited state, and we can distinguish one if it is at excited state. So because of their distinguishability, their microstructure will increase by the uh, n fold. The number of if n number of particles are distinguishable. So not n-fold, we can say it is definitely the higher than the uh, non-distinguishable particles. Okay, depends upon the problem, depends upon the states, and depends upon the combinations. Okay, so the third statement is of course wrong. So the option C must be the incorrect answer. Fine. So let's try to solve this problem. In how many ways can two indistinguishable particles distributed among two distinguishable harmonic oscillators in such a way that the total energy is fixed at 4h Dirac omega? So let's solve it because we just left 10 minutes. We are having two indistinguishable particles which are distributed to uh, let me uh, uh, so indistinguishable particles distributed among the two distinguishable harmonic oscillator. There's a harmonic oscillator H1 and H2, and the total energy is fixed at 4h Dirac omega. Right? 4h Dirac omega in the sense we know harmonic oscillator uh, energy is it depend upon the quantum number n is n plus 1 by 2 h omega, h Dirac omega. Fine. And n runs from, oh, sorry, n runs from 0, 1, 2, 3, so on. And the ground state for the simple harmonic oscillator, we will say H1 is, and there is a no degeneracy in this case, but because we are using H1 and H2 to harmonic oscillator, because of that the degeneracy may appear. So H1 will be having energy of uh, let's say quantum number 1 will be 1 half h Dirac omega. Similarly, quantum number 2 will be 3 by 2 h Dirac omega. Quantum number 3, oh, sorry, quantum number 3 will be, sorry, quantum number 3 will be 5 by 2 h Dirac omega. Quantum number 4 will be 5 by 7 by 2 h Dirac omega, and so on. And similarly, S2 or H4, H1, 5 by 2 h Dirac omega, 7 by 2 h Dirac omega. And similarly, S2, 1, H2, 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 4 is in similar cases, it's 1 half h Dirac omega, 3 by 2 h Dirac omega, 5 by 2 h Dirac omega, 7 by 2 h Dirac omega. And this energy will be in their combination, the total energy must be 4 h Dirac omega. So, so that and these two indistinguishable particles are distributed among these two harmonic oscillators. If one particle is distributed in H1 and H2, one is in H2, then we need to take that combination which yielding energy, constant energy, total energy as a 4 H Dirac omega. So we will check. So if you see 3 by 2 plus 1 by 2 should give you 4 by 2, which is not 2 H Dirac omega, which is not the fixed energy. But if you see uh, 3 plus 5, 5 plus 3, 5 plus 3 and 5 plus 3, 8 by 2, which is 4 Dirac omega. So H1 at quantum number 2, H1 2 plus, so it's not working. Fine. I will write here. So H1 1 is, let's say, H1 3, let's say 5 by 2, H Dirac omega, H1 H2, H2 uh, 2 will be 3 by 2 H Dirac omega. Similarly, H1 2 and which is 3 by 2 H Dirac omega, and H2 2, H2 3 is 5 by 2 H Dirac omega. Okay, this will fulfills the condition. Similarly, we can say 7 by 2 and 1 by 2. That also fulfills 7 by 2 plus 1 by 2 H Dirac omega will be 8 by 2, which is 4 H Dirac omega. Similarly, H1 4 is equal to 7 by 2 H Dirac omega. H2 1 is 1 by 2. Similarly, H1 1 is 1 H Dirac omega. These are 4 combinations we are getting. H2 4 7 by 2 H Dirac omega. And we need to distribute 2 distinguishable particles in the same. If you increase the, say, let's say, the next will be, next state will be 9 by 2 H Dirac omega. And similarly, it's not possible to have, because the energy for only one particle is exceeding with 9 by 2 means it's greater than 4 H Dirac. So only at quantum number 4, uh, it's possible. Uh, sorry, its quantum number should be 0, 1, 2, 3, 4. Up to quantum number 4 are possible. 0, 1. Sorry, up to quantum number 3 are possible. 1, 2, 3. Similarly, I need to change here also. This will be 2, 1. I just missed the index. So 1, 2. Here 3 and 0. And this is 0 and 7. So, so each time one particle can occupy uh, one harmonic oscillator, and uh, so the total number of combinations we will be getting is, because the indistinguishable particles are there, so we'll be having 4 different combinations. We are having 4 different combinations, and for the total energy fixed for H Dirac omega. as we are distributing two particles. So your answer should be 8. So there are four combinations and two particles. The answer should be 4 cross 2, which is nothing but 8. Fine. So, so thank you very much for attending the session. Uh, this one is the last problem. This is already we have solved. So we'll meet next week. Similarly, Tuesday, 7 to 9. So thank you very much for that ending the session. I'm concluding. I'm just ending the session now. Thank you very much.